Welcome to the Digital Tech Quantum Technology Insights webinar. We've got a packed schedule today. I'll just pop the agenda up for you there. With presentations coming through from Heriot-Watt University, Strathclyde University, Quantic and Chroma City, as well as a panel at the end. Slides will be available after the event, so if you'd like a copy, please send an email to edinburgh@eitdigital.eu. The event is also being recorded today, and we'll be sending that link out as well. And finally, there's a question section just on the right-hand side of your screen, so we encourage you to interact. Your question won't automatically pop up in the panel below. That's because we've got a moderator at our end, but don't worry, it has been received. So without further ado, our first speaker is Martin Beaton. So Dr. Martin Beaton is EIT Digital's Satellite Manager, where he leads the Scottish satellite of EIT Digital, which is a €70 million per year EU-supported funding organisation investing in co-funded industrial research, commercialisation of innovative technology and scaling of fast-growing companies across Europe. So without further ado, I will stop sharing my screen and pass over to Martin.
Thank you, Mel. Can you hear me? I'm going to assume yes. Yes, I got a thumbs up. Wonderful. I shall share my screen. Give me one moment. Right, hopefully you can see full screen. I'm sure Mel will text me if there's a problem at all. Thank you everyone for joining us today. This is very much experimental from our point of view. Thanks Mel for pulling it together. The original plan, for those that know EIT Digital and have followed our progress since we started last April, was to run regular events. We find them very useful from a networking perspective, and I know that a lot of good contacts and initiatives have been kicked off from the events that we've run up to this point. Obviously, under the current circumstances, we can't do face-to-face, but we wanted to keep that momentum up. Quantum is one of the areas that I profess have zero expertise in. When I did my undergraduate chemistry degree at University of Glasgow, I remember there was a module in quantum, I think maybe in our third or fourth year. I think it was only a few weeks long, and I have to say that I went into the class very excited, thinking this is going to be amazing, I'm going to understand the fabric of the universe, etc. And I think within 15 minutes, I was looking at the guy next to me, utterly perplexed. So it's wonderful we've got people here who actually understand it. I am very excited about the potential, obviously, for quantum going forward. And the idea behind this particular event is, can we take quantum can we understand, first of all, what the state of the art is at the moment, particularly within Scotland, the UK, and in Europe? And is there ways that we can apply that knowledge that where it exists at the moment into more traditional innovation? So that's the hope. That's what I'm hoping that we can get out of this. It may well be that after we've gone through the process of understanding a bit more about what's happening, maybe it's not practical. Maybe there isn't anything we can practically do, but I have a sneaky feeling that there is. So that's kind of the idea there, is that will couch what we're planning on doing over the next hour and a half or so. What I'm going to do very quickly, because this is essentially the less interesting part, you might argue, and just give you a little bit of background about EIT Digital for those that don't know anything about it, but I'll scoot through it very quickly so we can get on to the meat of the event. We've been through the agenda already, and I think there's probably nothing else that I can add to this at point. So, EIT Digital, pan-European organisation. When we set up in Scotland, it was very much of the knowledge that Brexit was on the way, and the purpose is help Scotland and to help Europeans innovate cross borders, bring the very best of academia and industry together to break new ground, to create new products, ideally with a global impact. EIT Digital itself has got 5 focus areas. You can see them on that slide there. In Scotland, we have particular strengths in digital finance, digital tech. Digital well-being is an area that we're exploring a little bit more. Obviously, there's actually a very vibrant sector. It's a very vibrant sector in Scotland, and we're working with a number of different partners. Digital cities and digital industry maybe a little bit less so at the moment, but it may well be that not really dug properly into these particular sectors in Scotland yet, because we haven't been operating in Scotland for all that long. I like to describe EIT Digital from an activity point of view as having 3 main threads or 3 main strands, and they all build on top of each other. So the first one is the creation of talent and intellectual property, I guess, through research. And to do this, EIT Digital run the EIT Digital Academy, and as you can see along the bottom there, there's kind of 4 different components to that. Particularly from a Scotland perspective, we're really focused on the digital doctoral skills. So in this situation, EIT Digital, in appropriate circumstances, will co-fund PhDs that are industrial, that have industrial outcome and are led essentially by industry. On to very briefly talk about what we've got going in Scotland in that area later on. But we're also running across Europe master's schools, and hopefully we can get some of these going in Scotland soon as well, along with summer schools and professional schools. And building on that, we have the innovation co-investment piece, and the call, I'll talk about it briefly in a moment, but what we have here is support from EIT Digital. It's an annual call. One's running at the moment, closes on 7th of May, where we're supporting organisations and universities that are spinning out, have innovations they want to productise, supporting them to apply for grants. Not for grants, sorry, for co-investment from EIT Digital. So EIT Digital will get involved and help these organisations commercialise with funding from EIT Digital. We're going through that process, as I say, at the moment in Scotland. And then, so as you can see, we've gone from university research into supporting the commercialisation of that research. And the final piece is the EIT Digital Accelerator. So this is to support companies that are already doing good business. They've already got very solid, made a solid impact within business, and that's to help them to access new markets across Europe and access finance from commercial investors. So that's kind of encapsulated the 3 kind of main threads that EIT Digital get involved with, right up the stack, as I say, from university innovation all the way up to, or creating new innovation all the way to hopefully creating very successful companies or even unicorns across in Europe. So we always talk about the EIT Digital ecosystem, and I do believe that's one of the most powerful aspects of EIT Digital. So EIT Digital has locations, offices right across Europe. I think there's 17 locations currently. You'll see Edinburgh and Boulder, one of the newest ones, having set up last April, and also a presence out in California in San Francisco. What you have there is, well, one of the things I particularly like about it is you can't take on a role or a senior role within an EIT Digital node or satellite unless you've got a really good understanding of the academic ecosystem and then the industry ecosystem as well. And ideally, you've got a good understanding of how the government works, etc., and good contacts into there. So by having all of these satellites, all of these nodes, all these presence across Europe, from our office in Scotland, we essentially have a network of networks. So we can contact the Paris or the Helsinki node and say, do you know company X? Or in fact, we may already know that they know company X because they're part of our industrial ecosystem. So what I mean there is that a community of companies join EIT Digital. There are over 250 organizations and institutions that are already members of EIT Digital, actively participating in the programs that we run. It's very simple for us to put these companies in contact with each other and make things happen. And indeed, that's what we're doing at the moment with the call that we're running companies in Scotland that are looking for a consortium partner somewhere in Europe, it's very simple for us to reach out to one of our colleagues in one of the other European offices and ask them to be put in touch with a particular industry partner that we have an existing relationship with, or indeed a company that we don't have a relationship with, but the staff within the office know them or can facilitate an introduction. So very briefly, the Scotland office is kind of unique. We were set up last April, as I say, so that's Ivan McKee, Cabinet Minister for Innovation, who is shaking the hand of Willem Jonker, who is the CEO of EIT Digital. There are 6 organisations. I'll take back a step. In order for us, a node, so our UK node is in London, in order for a node to set up a satellite in another area within the country that they're in, we need the welcome of the ecosystem. The ecosystem needs to demonstrate that it would like EIT Digital to have a presence there. So the 6 organisations that were involved in Scotland are on the right-hand side there. So Scottish Enterprise and Scottish Funding Council, core funding partners of the EIT Digital Office in Scotland. Edinburgh Innovations and Edinburgh University, also core crucial contributors to EIT Digital in Scotland, and Highlands Islands Enterprise and FinTech Scotland. Across these 6 different organisations, we have underpinned the entire ecosystem of Scotland, and it's wonderful having these partners, and I really can't underestimate how important they are. The office itself was set up with, next slide there, with 2 doctoral training centres at the University of Edinburgh to begin with. So if you remember, doctoral training centres, EIT Digital fund 50% of the PhD costs. So we had 2 when we started up in Edinburgh, one in cybersecurity and one in fintech. Since then, we welcomed Napier University on board in January. So we also have a doctoral training centre in aspects of cybersecurity. And we're working very closely with a number of different universities, University of Glasgow being one of them, Strathclyde, conversations with Heriot-Watt. In fact, most of the universities, certainly across the central belt at the moment, but our remit is the whole of Scotland. It's just really been a case of timing, really. So we fully plan to speak to all the universities in Scotland to see if we can get initiatives going. Also, on the innovation funding point of view, as I mentioned earlier, closing date is the 7th of May. We have had a huge amount of interest. Over 50 companies initially were interested in funding when we started the process of talking to companies back in October, November last year. We have substantially more companies applying this year in Scotland than we did last year. And I'm very excited to find out in June or late June how many of the Scottish companies have been successful. So that's what we're spending pretty much 100% of our time at the moment in Scotland doing, is supporting these organisations that are making the applications, helping them to refine and polish the proposals to give them the best possible chance of winning the funding. So that takes us all the way back round to Quantum. As I say, a passion of mine, although I don't understand it particularly. So Quantum itself sits within the digital tech focus area in EIT Digital, and you'll see I've very clumsily highlighted the area of quantum computing here. So it's absolutely not a core part of EIT Digital focus at the moment, but it is referenced. And I think the assumption is that there's a strong feeling that quantum will become a bigger force within the digital tech focus area. At the moment, it's a little bit on the fringes, and that's essentially why we want to run this event, is to explore that inverted commas fringe, and I don't mean any offence by that, technology area, and see if we can see what we can eke out and maybe make it a little bit more mainstream going forward. So that really summarises EIT Digital position, at least from Scotland. If you would like to contact me, there's my email address. Our office is in the Bay Centre. It's currently empty, except for probably a couple of dead or dying plants. But we hope to be back there very soon. Other than that, we are entirely available online if you would like discussion, talks, anything you want to know about EIT Digital, any support that you need. let us know. We are here for you. And I think with that, I will pass over back to Mel and hopefully move on to the next presentation.
Thanks very much, Martin. Right, so I'll just pop the agenda up so that you can see where we are in proceedings. Bear with me 1 second. There we go. So next up, we have Dr. Ross Donaldson. Ross is from Heriot-Watt University. He's a Royal Academy of Engineering Research Fellow there, having previously completed a postdoctoral research position in satellite quantum communications. So I'm just going to stop sharing my screen. Sorry, apologies, this is a little clunky. And go ahead, Ross.
Thank you very much, Mel. I'll just load up my slides. You should hopefully see everything okay now. Okay, so first of all, thank you very much for the invitation and for everyone attending as well. These webinars are actually making it much easier to attend a lot more conferences to find out a lot more about what everyone else is doing. So as Mel mentioned, I'm Dr. Ross Donaldson. I'm a Royal Academy of Engineering Early Career Research Fellow who was funded back in 2018. I teach in the School of Engineering and Physical Sciences, particularly in physics, and also researcher in the Institute of Photonics and Quantum Sciences. And I'm going to be telling you a bit more about that research institute today. So the aim of today is to talk about quantum technology at Heriot-Watt, but also give those who are maybe not too familiar with quantum technology a little introduction. So quantum technology itself, maybe this will help Martin a bit with understanding quantum as well. So really there's a few generations of quantum technology research going on. And this actually, the first generation of quantum technology really stems back to the 1940s, where quantum phenomena was starting to be understood and applied in real experiments. So quantum phenomena such as atomic spin, quantum tunneling, or anything really to do with quantized energy levels. And DSTL termed these technologies quantum 1.0. So few examples of those technologies themselves. So we have MRI scanning, which allows us to very quickly scan and then diagnose diseases. I think many of us in the audience are from the photonics and optics sector in Scotland, and without the laser, a fundamental quantum technology, we wouldn't have any jobs today. And you know, the digital economy wouldn't exist without semiconductor technology and transistors, which inherently rely on quantum phenomenon as well. So although Martin said that quantum technology is on the fringes, it really is a quantum technology to start with. And I think we can all agree that the first generation of quantum technology has had a massive effect on the way society is today in terms of social as well as economic. And as time has gone on, there's been a second wave of generation of quantum technology being developed, which is based on other quantum phenomena, which has been studied in depth and been put to experiments as well, such as quantum superposition and entanglement, quantum uncertainty relations, and also quantum correlations. And these technologies are dubbed Quantum 2.0 by DSTL as well, and incorporates technologies such as quantum computation, quantum communication and the networking, quantum imaging, and also quantum sensors and devices such as quantum random number generators. And really the hope is that the second generation of quantum technology is going to have as much of an impact or more of an impact on the way society is today. More of an impact than the first generation of quantum technologies. And really the UK was a leader in developing quantum technology programs for pushing the research from research labs out into industry through its development of the National Quantum Technology Program, which was a 5-year program funded through the EPSRC, which started in 2014. And really this was a £120 million worth of research investment with additional investment on top of that from companies. And the aim was to look at 4 quantum technology areas and create hubs which focus research on those areas. So there's 4 hubs highlighted at the bottom. Each of these were led and administrated by a university, but all the hubs involved a number of university partners in them. So going from the left-hand side, the University of Oxford led a hub which looked at quantum computation, simulation, and also quantum networking. The University of Birmingham led a hub which revolved around sensors and metrology, particularly looking at ways of navigation that didn't require GPS, and also creating really sensitive sensors which could, for instance, identify or map roads looking for pipes. So the aim is to reduce the number of traffic jams that you're in on your way to work. The Quantum Communication Hub, which is led by the University of York, looks at having quantum equivalent communication protocols, which are said to be more secure than conventional communication protocols. And finally, the Quantic Hub, Quantum Enhanced Imaging Hub, led by the University of Glasgow, which you're probably going to find out more about in a later talk, which is all about using quantum phenomena to enhance the sensitivity of imaging. And these hubs were so successful that, in fact, there has been a second wave of funding for them of £94 million, and that second wave started in December of 2019. So getting back to Heriot-Watt, the Institute of Photonics and Quantum Sciences was set up in 2012 as part of a wider university initiative to focus research areas. And as the name suggests, it was set up to focus on photonics and quantum science research. And really this was taking advantage of and building on experience of more than 40 years researching in the photonics and optics sector, including, if you've ever been to Heriot-Watt, you might see an optical computer up on the wall as a kind of history of what Heriot-Watt was involved in the 80s and 90s. So the Research Institute is currently led by Professor Patrick Oberg, who is a quantum theoretician. He leads a staff of more than he leads a team of more than 30 academic staff, who in turn supervise and manage more than 50 postdoctoral researchers and more than 110 active PhD and engineering doctorate students. I should hide that. That will probably give everyone a better view. So the research at Heriot-Watt in particular, the Institute of Photonics and Quantum Sciences, is really applied. So the university has strategic alliances with companies such as Leonardo, Renishaw, and AWE, primarily looking at the photonics research in the institute, although these companies are starting to get more interested in the quantum sector as well. The university has a number of successful spinouts in photonics, talking about Heliophotonics, Edinburgh Instruments, Power Photonic, and also Chromatity, who you're going to hear more about in later talks as well. You know, as well as large collaborations and spinouts, the university also boasts a number of R&D projects and R&D funded projects with a number of other companies as well. And this just gives you an example of the type of companies we currently have either partnerships with or work with on collaborative R&D projects. As well as the project side, the university also hosts and administrates a Centre for Doctoral Training in Applied Photonics. And this is an EPSRC co-funded engineering doctorate program, which involves 6 universities from around the central belt of Scotland. And all these universities have very well-established research groups in applied photonics. And these are 4-year funded programs which allow a student to have PhD level projects in R&D with technical and MBA courses as well, allowing them to understand the fundamentals of the research requirements, as well as having the training so that they can conduct and manage industrial R&D projects. So the students spend 75% of their time in the company, so they really are acting as an R&D team for the company, and 25% of their time is in training. Quantum projects are welcome to this Centre for Doctoral Training. I myself have an engineering doctorate student in a company in Glasgow who is working on quantum communications, and I know there are at least 3 other projects which are revolving around quantum in some way. So quantum technology at Heriot-Watt itself, I mentioned there were 4 hubs set up for quantum technology research, And academics from Heriot-Watt played leading roles and still do play leading roles in two of the hubs, the Quantum Enhanced Imaging Hub and the Quantum Communication Hub. And I would say these are the two areas of expertise in quantum technology at Heriot-Watt. There are over 20 academic staff who contribute to quantum technology research, where more than 20 of the postdocs are specifically on funded projects for quantum technology, with more than 30 PhD students working on quantum technology research as well. So you can see out of the wider institute, there are a majority of members of staff are contributing to quantum technology research, specifically in imaging and communications. As well as funded projects, the EPSRC and Royal Academy of Engineering have also awarded a number of academic staff with fellowships, demonstrating that there are a number of world-leading researchers in quantum technology areas. The university has also supported more than £15 million worth of projects in recent years, and has itself invested more than £2 million worth of internal money. And this money has gone to paying for refurbishment of labs, creating new labs, and refurbishing general research facilities such as the Nanofabrication Center, which is used for creating quantum sources and fabrication of quantum detectors. And of course, that investment is going to continue to keep coming as UKRI looks to invest more in quantum technology research. So there are a number of calls in the Industrial Strategy Challenge Fund run by Innovate UK, which involve quantum technology research. Oops. And Heriot-Watt is involved in a number of those and will continue to be involved in those in the future. There is also a number of academics working in projects from the Quantum European flagship as well. So in terms of a general overview, of those 20 academic staff, 12 of them, well, there's 12 groups made up of those 20 academic staff which focus on quantum research. This ranges from a number of areas, such as quantum sources, looking at creating entangled sources at different wavelengths and creating more efficient quantum sources. Also looking at 2D materials, which can be used for quantum sources. Once you have those quantum sources, looking at the applications that you can use them for, such as sensing, imaging, computation, or communications. And then, of course, after you've done your application, you need to have some way of detecting those quantum states. And there's research groups at Heriot-Watt which look at single photon sensitive detectors, taking it from fabrication all the way to testing and implementation as well. So really, at Heriot-Watt, we cover the range of quantum technology all the way from sources to the detection themselves, but also covering a number of fundamental aspects of quantum technology research as well. So possibly looking at ways to have a third wave of quantum technologies in the future by looking at condensed matter, cold atoms, additional ways of doing quantum computation, and additional ways of doing quantum communications as well. So just to give you a flavor of the kind of research we're going to be doing in the second phase of the Quantum Communication Hub, I've chosen this over any of the other hubs because I'm involved in the Quantum Communication Hub, so I can easily answer questions relating to it. So 4 areas of interest. One of them is led by Professor Anderson. She is leading the Heriot-Watt effort on looking at new quantum communication protocols, really expanding the number of quantum solutions to cover a number of things that are done conventionally. In the last phase of the Quantum Hub, she enabled a lab demonstration to be taken from the lab out into a real live quantum network in Japan over a 4-year development period. And I think she's seeking to do something like that in the next phase of the hub as well. Source and detector development is being led by Professor Buller. He's looking at germanium on silicon single photon avalanche diodes, basically offering a new semiconductor detector for infrared detection. Professor Buller, Professor Fujitsu, and myself are also involved in a work package which is looking at creating an in-orbit demonstrator, which is going to be used for satellite to ground quantum communications. We are looking at developing a payload, which is one of the potential payloads which will be launched. We are also designing and constructing an optical ground station, which we are hoping will be located at the Heriot-Watt campus as well. And finally, Professor Pedrizzi is leading the way on entanglement-based networking, so creating multi-photon entanglement states, looking at ways of creating more of them, and then how do you actually use them in practice? What communication protocols could you do, and does it offer anything else? So just as a summary, the Institute of Photonics and Quantum Sciences has an abundance of expertise in quantum technology, primarily in quantum photonics and specifically quantum imaging and communications. We're world leading in many aspects of quantum technology, and we have some fantastic research infrastructure to carry out research. We're also open to collaborative work, so if you've seen anything interesting in these slides or on the website, feel free to get in touch with the academics and research groups to arrange for a visit and start collaborative work. So thank you very much.
Thanks very much, Ross.
Thank you. I'll unshare my screen.
Perfect. Thank you. Okay. So yeah, it's wonderful to see the level of success that's happening across quantum technology hubs, and also the range of collaboration that's happening between industry and research institutions. So up next, we have Professor Jeremy Ward. Jeremy joined the University of Strathclyde in 2018 after 35 years of working for QinetiQ and its precursor organisations, ultimately leading to being CTO. At Strathclyde, he's leading the formation of a quantum cluster as part of strategic development program in the university. So I'm just going to stop sharing my slides and allow you to come online, Jeremy.
Okay, let's have a go. So hopefully you can see my opening slide. So
yeah, that's showing.
That's great. So thank you very much for inviting me to talk today. So I've taken a rather broader view as to, well, what's the state of the art in quantum technologies at present and what might happen in the next few years. So this is not particularly UK or Scottish based, but it's what's happening quite broadly. And just see why I'm not being able to advance the slides. 1 second. So we're going to look forward for the next few years. So firstly, let me say I'm not a world-class quantum physicist, so I've made no predictions about what might change in quantum technologies. And very much in the way that Ross was describing, these are things that are in, let's call it quantum 2.0. And in particular, those four topics that, what makes something quantum 2.0. It's essentially things that, things like this wave-particle duality. So something can be both can behave both as a wave or as a particle. You can have superposition, so something could be in one or more states at the same time. This weird thing called entanglement, where you do something to one particle and something immediately happens to its pair. And then finally, the whole concept that if you measure a quantum system, you're effectively changing it. And that's so it's quite difficult. You have to think very carefully about what are you measuring, what are you creating. So really, typically, these are the sorts of things that we're interested in quantum 2.0. So you'd be pleased to know that's the end of what's quantum that I'm going to talk about. So thinking about what's happening out in the world, I've looked at other people's roadmaps. There's a couple of slightly older ones here, and the next couple of slides I'll include references. But these have been three very useful sources. So firstly, the UK quantum technology programs, essentially the precursor to the first wave of hubs described by Ross. it's out of date, but it's a useful overview. Perhaps more interesting is a European community roadmap. There's been a couple of iterations of this. If you click on the final slides, you'll see it should hyperlink to on the picture of the screen there. And this breaks it down into 4 quantum opportunities into 4 areas: communication, computation, simulation, and sensing and metrology. So, and I've chosen to structure what I'm going to talk about basically the same way as this report. And I would recommend this. This is a read. I wouldn't say it's an easy read, but it's quite some interesting predictions in it of what might happen in each of the areas. So I'm going to start by talking about communications, so essentially much the same topics that Ross covered. I started with communications because I think that quantum communications is the closest to market and the things that we'll see happening first. And what we're mainly talking about is something called quantum key distribution. And what it is essentially a secure way of sharing a secret between 2 parties. It itself is not a cryptographic technique, and the advantage of using quantum techniques is that you can effectively guarantee that you either receive the message or you know that it's been intercepted. Now, typically the way it's used is, at the moment, is to exchange keys or encryption keys by this method, and then use those keys to encrypt some form of standard communications channel. Now, there are other things you can do with this, using one-time keypads. You can produce provably secure ways, but the idea of exchanging keys in a secure and provable fashion is really what's at the heart of quantum key distribution. And don't worry about too much about the words, but broadly speaking, there's 2 ways we can do this, or how can we distribute these keys. We can either do it on the ground, typically either through the air or through an optical fiber, or you can do it, as Ross mentioned, through space, or via space. Now, there's a lot of groups interested in this sort of activity, but if you thought that the distance you could send these keys is getting into the hundreds of kilometers now for reasonable data rates on the ground. But interestingly, China, and that's a picture of the satellite they launched to do this via space. So it's Chinese is sometimes called the Mikius satellite, and they launched it in 2017. And they've managed to demonstrate doing the exchange of these keys via space. The great advantage of that is it gives you potentially a really long range, potentially the basis of worldwide communications. There are many difficulties you've got to overcome, but nevertheless, it's the start of a very long range, secure communication system. This is a list of some of the things that the comms hub that Ross mentioned has concentrated on so far. And this is, you could probably summarize this as establishing networks, actually using these key distribution schemes, reasonable distances, Cambridge and Bristol by London, nodes at Cambridge with BT near Ipswich, and also trying to miniaturize these modules to do this key distribution, so you could incorporate it into things like mobile phones. So, really interesting program, and they've got more to do in the next phase. So, what do I think might happen in the quantum comms world QKD world in the next, say, within 3 years, and then say more than 3 years? Well, I think within the 3 years, we're going to see potential deployment of these systems in urban areas, metropolitan areas. There's probably a standardization effort to happen. Quantum random number generators are certainly going to become much more prevalent. And we're going to start to see people producing schemes for getting the range up, either by repeating the signal, which produces some trust issues, or using drones flying on the edge of space, or using satellites. And a bit like Ross's work, you'll probably see the first CubeSat implementations of quantum key distribution. I think in the longer term, we'll see QKD becoming available through the air, say from mobile phone masts to an end user. Now, the range is going to be really quite substantial, and we're going to see these things starting to become much more prevalent. And I think, others might think it'd be quicker, but formal proofs of the security of these systems will become available. So I'm reasonably optimistic that quantum comms will be one of the first and quite transformative applications of quantum technologies. So I'm going to turn to the second of my topics, essentially quantum computing. And it's actually going to be computing and simulation. Now, broadly speaking, there are two ways that we approach quantum computing today. What pretty well everybody's trying to do is trying to make a gate-based quantum computer which works in a sort of similar way to the way we think about conventional electronic or logic at present. And the picture on the right is a picture of an IBM machine trying to go down this route. But for reasons that I'll explain in a moment, gradually explain, trying to make the qubit or the bit, the primitive that's at the heart of the digital quantum computing is really rather hard. Making a lot of them and making good ones is really hard. The alternative approach is essentially to do analog computing. So those are old enough to remember, early days of electronics. There was always digital electronics, but there was always first analog computing. There's an analog circuit. There's a similar analogy here. There's a number of different more analog approaches. And you may have heard of a company called D-Wave who make, let's call them analog machines. These are typically used for simulation and optimization problems. So how far are we down this route? So this is quite the reference here is I recommend is quite a good read. It's not a difficult read. It's quite a substantial tome. It's written by the US National Academy of Sciences. It's their report from right at the end of 2018, beginning of 2019, on the progress in quantum computing. And it's a really interesting and even-handed review of how difficult quantum computing is going to be. And these are I'm going to start this section by talking about their conclusions, and then talk a bit why are these conclusions the way they are. They don't really know how long it's going to take to make a scalable, and that means a big quantum computer. And we'll talk a bit about what I mean by big in a moment. At the moment, you can really count qubits, and that's okay in the short term. But in the longer term, you've got to think about how well these qubits work, and making a larger scale useful digital quantum computer is a combination of, firstly, making qubits, but secondly, make sure that they work well and do not generate errors. Oops. Right. So this may not come over too well. This is a diagram from that report, which essentially is a roadmap of how to get from where we are today, which is the bottom two boxes of tens of qubits in a gate-based quantum computer, right up to the top, as the box with a star at the top, to a large-scale fault-tolerant digital quantum computer. It's a long route. This is a really quite a tricky thing, and arguably we've made it up one box on the right-hand side there, with Google declaring last year that they'd reached what they call quantum supremacy, i.e. being able to do a computation that couldn't be done any other way in the life of the universe by any machine on Earth at present. We've arguably got to that box. There's quite a lot. What I'm trying to get over to you is there's quite a long way to go to get to a large-scale, useful digital quantum computer. So it's going to run through some of the approaches that people are taking to, technical ways of doing that. People are trying to do this at present. I should thank my colleague Andrew Daly at Strathclyde for these next 3 slides. So the thing you've probably all seen most of are the publicity from the likes of IBM and Google and a company called Rigetti, talking about qubits made on a superconducting basis, and they've all got to 50 to 60 qubit type of, despite spending a lot of money, they've had trouble scaling that to make it a bigger machine. Another approach is called trapped ions, and this is particularly Honeywell, and there's quite a few groups going around the world, and also Oxford and the UK Quantum Information Technologies Hub has been particularly interested in a trapped ion approach, and that's good. That's this is in the range 50 to 100 qubits at present. Another approach, which is one we're adopting at Strathclyde, is to trap atoms using lasers. So your qubit is a laser, and this is perhaps becoming a I think well, of course we would perhaps say this because we're doing it, but we think this has great potential to scale, and we are very fortunate to have a prosperity partnership led by between ourselves and M² Lasers to build such a machine, starting with 100 qubits, but the design scaling to perhaps at least 1,000. In many ways, this is a much easier approach to build, and we're quite optimistic that it will produce high quality qubits. This final slide here suggests 3 other approaches being considered around the world: silicon qubits, photons, in particular this company PsiQuantum, which has raised a lot of money, and then there's been a scope for manipulating vacancies in diamond for the qubits. So really, there's a huge range of still research topics to, well, what's the best way of making this? A lot of money is going to those superconducting qubits, but it's really hard to make a big practical machine. Let me just swap slightly over to simulators. So instead of trying to make a digital algorithm, you could do a simulation, and there's lots of different ways of doing simulation. It could be simulating arrays of atoms, it could be materials properties, flows, and there are many ways of doing this simulation. My guess is that the first practical applications of quantum computing will be in the area of simulation. And if you go back far enough, the original idea from Feynman was essentially, this is how Feynman thought of quantum computing. So what do I think about quantum computing? I don't think there's going to be a general purpose quantum computer available within 5 years. Yes, there's some stuff available on the web, cloud-based access, but they're still quite small machines. And it's only going to be for the first, only some very special problems are going to be tractable for quite a long time. So there's no, in my mind, I don't think ever that our approach to conventional computing will be replaced by quantum computing. Quantum computing is going to be great at some very specific and difficult problems, but it's not a general purpose scheme. I think simulations are first. But also worth saying that the algorithms to exploit quantum computing are themselves really quite hard to write. So I don't want to say this is all very difficult. It isn't easy, but there's work to do here. So let me turn to the final area, sensing and metrology. So there's lots of quantum-based sensing schemes possible. And really the reasons you're doing it is you want to make a better sensor that's more sensitive than the classical sensor. You want to do things that are smaller in size and power and weight. The array on the right, the picture on the right is from NIST, the US equivalent of the National Physical Laboratory, and that's an aluminium ion-based clock, which is about 1 part in 10 to the 19, an amazingly accurate clock, quantum clock. Again, a slightly older roadmap, but this is from the Metrology Hub's roadmap when they set up, and it's still really valid. If you look across the middle sort of pink line, you can see that we on 2020 they've thought some big sensors, hundreds of watts, gradually getting smaller, aiming in a decade to sort of consumer-based sensors. I think that's broadly still right. So just as some examples, again, Ross mentioned a gravity sensor being developed at Birmingham. So that wonderful tube on the right is there. You can use that for, it's quite a sensitive measure of gravity. So looking for mine shafts, anomalies, voids underground. You can use it in space. There's lots of things one perhaps could do sensing gravity from space, for example. A difficult thing, a really quite a difficult engineering challenge to build this, and I wouldn't say the physics was easy either. The other end of the spectrum, some work at Strathclyde is on producing a quantum magnetometer. This is what's called an optically pumped magnetometer. Don't worry about how it works, but it's a pretty sensitive magnetometer. Those essentially, it's a few picotesla per root hertz for people who understand it. Let's build this. So the sensor itself is tiny. There's not very little in it. So that white box with a Q on it, it's about the size of a matchbox. The two connectors on top are RJ45 connectors for scale. And it's really quite a sensitive thing. We're testing it out there at Ross Priory by Loch Lomond because it works unshielded in the Earth's magnetic field. There are many applications for example, sensing heartbeats or brain waves, detecting targets. Lots and lots of applications. You've got to think very carefully about the environment you use it in, because there's many sources of interference, like railways, motor vehicles, high voltage power lines. So they're not the easiest things to use, but it's a really sensitive and a tiny thing. And that's just an example of detecting a drone taking off, and you can see the harmonics in the electric motors. So that's been developed with funding from the Birmingham Hub. So what do I think about quantum sensing? So I think we're going to see smaller, more stable, robust and practical devices, and there's going to be thousands of applications, hundreds of applications. And really, just to finish, this is a prediction of the markets that the Metrology Hub thought about for sensors. And you can see these are huge worldwide markets. I'm not saying that there's sensors of ideal sensors in every single one of these areas, but it gives you a feel for the large scale applicability of these quantum sensors and measuring schemes. And some of this could be really quite transformative. So thank you very much, and happy to try and answer questions at the end.
Thank you very much, Jeremy. That was an absolutely fascinating talk, and really good to have a bit more of an insight into the near future of quantum technologies. Apologies, I'll just get the agenda up again so that we can see what's coming up next. So next up, we have Yash from Quantic. Yash joined Quantic in April 2020. He's responsible for business development, commercialization, and marketing. Yash has worked in leadership roles for both SME and Fortune 500 companies and brings a strong industrial focus. He's led global R&D, technology, business development, and marketing teams, and he has been a member of several advisory panels involving the EU Commission, BEIS, Scottish Government, and the Infrastructure Commission. Yash was instrumental in setting up and commercialising the National HVDC Centre and led various Horizon 2020 and Innovate UK programmes. He's passionate about quantum technologies and experienced in helping industry and academia with innovation, VC and seed funds. So without further ado, I shall pass the screen over to Yash.
Hello, everyone. Thanks to the organizers and all the attendees of this webinar for inviting me to speak. I'm responsible for business development activities at Quantic, which, as Ross already described, is a quantum enhanced imaging hub based at University of Glasgow. My aim today is to give you an overview of the innovations in the field of quantum computing, and I will just see. Sorry, I'm just trying to share my screen. I just realized that the screen hasn't come up.
Yes, if you're having technological troubles, I can share the screen for you and you can tell me to skip on to the next slide if you prefer.
All right, yeah, let's do that.
Okay. Okay, just tell me when you want to go to the next slide.
Yeah, thank you very much, Mel. I hope everybody can see it now. So I want to give you an overview of technologies developed at Quantic and some of the other hubs that are part of the National Quantum Technology Program, and also their funding landscape. Can you move to the next slide, please, Mel? So the UK National Quantum Technology Program was announced by the UK government in 2013 and was established with the purpose of creating a quantum industry within the UK. The vision was to bring together government, industry, and academia to give UK a world-leading position in the emerging multi-billion pound quantum technology market. For this, EPSRC funded investments in 4 hubs, of which Quantic is one. During the same period, the UK launched its new industrial strategy, which provided a funding of another £451 million from Innovate UK. So that's a total £1 billion funding landscape. Could you get to the next slide, please, Mel? So these are the 4 quantum hubs. I won't go into much detail because Ross has already given a flavor of all the 4 hubs. What I would say here is that each quantum hub is addressing a specific issue of quantum technology. For example, we at Quantic focus on the quantum enhanced imaging that is used to develop technology to solve real world problems and imaging across industry, scientific, security, and consumer markets. So these technologies include visualizing invisible gases, detecting objects around a corner, seeing through rain, fog, murky water, and also visualizing through the body. The Quantum Technology Hub, another one which is based in Birmingham, developed sensors that is used in geophysics, healthcare, and navigation systems. The quantum communication hub, which Ross described in quite a bit of detail, is based in York University and is mainly pursuing quantum communications, the KQD technologies, which was spoken about by multiple speakers. The fourth hub is at the University of Oxford, which is the Quantum Computing and Simulation Hub. It's focusing on developing hardware and software systems for future quantum computers and simulators. Can you go to the next slide, please, ma'am? So Quantum has a partnership with 8 universities, which you can see on the slide. Our aim is to closely work with industry partners to accelerate commercialization of the technologies developed through these universities. Next, please. We work with various industry partners across these number of sectors, which you can see on my slide. We do this by offering either a novel solution or enhancement to an existing solution, or offer a cheaper alternative, or even combination of all of them. Next, please. So here you can see an example of deep learning real-time single pixel video based on SPAD technology created at University of Edinburgh. We have developed a single pixel camera. It can record more compact images, which you can see on the right-hand side, and process the data on an external computer, which reduces the camera's power requirements. These single element sensors measure infrared, UV, and terahertz radiation, which would be far cheaper to make than multi-pixel arrays. They could, for example, be used to make night vision cameras. Single pixel cameras also speed up pattern recognition systems, and especially can apply ML to the pattern recognition tasks. The conventional imaging systems produce human visible images that are then given to computer to analyze, but there is no need to generate a human visible image because computers can analyze directly the raw data, which in fact speeds up the whole process. So this technology is currently adapted for autonomous vehicle LiDAR systems. Can you go to the next slide, please? The other area of interest is security and defense. Our researchers have been working with a number of UK defense-related organizations and developing technologies for covert or unspoofable operations. Some of the applications include detecting movement of objects or people around walls, seeing through camouflage, and seeing under the murky waters. Next slide, please. So one of the other areas looking around the corners, and this you can see the instrument our researchers are using. These are spatialized cameras which send out laser pulses that illuminate a point on the ground in front of them. And this scatters the light, and the scattered light then hits an object which is lurking unseen around the corner. The light bounces off from this object and re-enters the camera's field of view, which is then detected. So by combining sensitive cameras with the computer algorithms, we can reveal these objects that are otherwise hidden from the view, enabling detection of objects or motion around corners. Such techniques can also be applied to image hidden objects within the body. Can you go to the next slide, please, now? So here what you're seeing is an example of this. You're seeing a beam of eye-safe light bouncing off an object and spreading in all directions. Like a pebble which is thrown into a pond, the waves go out. When any photon of light hits the hits another object, the light scatter gets rebounded and is scattered in all direction, which is just what's happening right now. A single pixel camera is then able to detect the rebounded light from the specified area. This time, by calculating the time it takes to reach the object and gets reflected, we can know about the motion of the object, both the shape and the size and the distance of that object. Our academic research team has demonstrated detections of humans behind a corner at more than 50 meters from the standoff distance. Machine learning is then applied to identify the person position behind the wall, and we have acquired an accuracy of around 85 to 95% in these experiments. The ability to know what is hidden around a corner or behind a wall can be quite crucial in many defense and security applications, and also automotive applications that we're looking for. Can you go to next slide, please, Mel? Another area of application is life sciences, the biomedicine. So quantum technologies techniques can be applied to microscopy applications to produce more efficient and faster detection modes, which will have impact on, for example, cancer detection. Using single photon counting techniques underpinned with machine learning, we are developing systems to image through the body. The great advantage is that this does not require MRI or X-rays, so it's quite useful. Can you go to next slide, please? If anyone has had to endure any medical procedure using an endoscope, you will know what the size and width of endoscope is and how uncomfortable is the experience. Conventional endoscopes contain typically 50,000 fibers when grouped together. It's rather thick, this whole assembly. But what if you could get all this data using a single thin fiber? Well, the issue with this technique is that the image that you get back is a gobbled mess. However, our researchers have found that by using clever algorithms, we can develop images, and using beam shaping, we can scan the output and detect the scattered photon, and roughly can produce a very good 3D image, which you can see is being built in this screen slide shown. Can we go to next slide, please, Matt? We are also developing technologies for applications in space, which is used for satellite communication and altitude control of nanosatellites, and this involves multiple companies and various other institutions whom we are working very closely with. Can you go to next slide? Some of the other areas which are being trialed are geophysics, monitoring volcanic activity, and viewing invisible gases, which I'm going to talk in detail now in the next slide. So this is a picture of a handheld single pixel camera. And what we have done is we have developed it, and it's made up of a standard command. Sorry. So what basically we do is using lasers, we tune it to a particular wavelength that matches the absorption spectra of a certain gas. And with this, it is possible to image that gas. So if you go to next slide, Mel, I will play a video in which we are detecting methane gas. So what you're seeing is a pipe filled with methane gas, and one of the joint is made loose. The histogram produced when detecting methane has been given a color, essentially, because methane is an invisible gas. The image is then overlaid on the top of a standard image to provide real-time imaging of gas, and with the help of this flame, you can then go and detect the exact position of the leak, which you can see through the flame. Can you go to the next slide, ma'am? So to know more about Quantic Technologies, please register for seminar which we are conducting. You can register for 1 day or more days by visiting our website, which is shown. And if you click under the events, you can see all the webinar series that we are conducting. Can you go to the next slide, please? I want to quickly touch base with the UK photonics industry and provide a landscape of the Scottish photonics industry as well. So the UK photonics industry contributes roughly £13.5 billion to the economy every year, and it employs about 69,000 people with a manufacturing productivity of £76,400 per employee. Focusing on Scotland, Scotland's photonics sector is a £1 billion industry supporting about 4,000 highly skilled jobs. Similar to the UK photonics market, the Scottish photonics sector is also a fragmented one, which means that it is dominated by a large number of small and medium-sized enterprises, where around roughly 80% of the revenues are generated by just 8% of the companies. Can we go to the next slide, please? So how can this vibrant community engage with digital sector in Scotland and wider UK? So one of the ways of doing this has been elaborated in the Innovate UK document, which is titled ElecTech Sector Roadmap for the UK, Enabling the Digital Future. This document shows that the key system level capabilities that form the building blocks of future digital solutions are sensing systems, which you can see on the left-hand side of the slide, the sensing systems, embedded computing systems, power management systems, communication systems, and autonomous systems. So for me, the synergy lies in areas such as quantum computers, sensing systems, single photon detection, and quantum sensors. Miniature quantum clocks have the potential to provide navigation information, especially in the absence of satellite-based systems, which might be under development as elaborated by other speakers, and underwater and inside the buildings. The other areas are lighter systems for autonomous vehicles and cybersecurity using KQD, which has also been highlighted. Can you go to the last slide, please, ma'am? So I hope that I have provided you an overview, a very quick overview of the quantum landscape in Scotland and across the UK. My key takeaway message is that there is support and funding available to work collaboratively to link quantum technologies with digital technologies. And I look forward to working with all of you. And please feel free to contact me at my email ID if I can be of any further assistance. Thank you very much.
Thank you, Yash. That was a great presentation illustrating how quantum really does underpin a broad range of different sectors. We'll also be sharing information on the quantum webinar series that Yash mentioned there from the 1st to the 5th of June in emails. So do keep sending your email addresses in via the chat function on the right-hand side. Don't worry, these won't be published for everybody else to see. That only happens if our moderator approves them, so don't worry about that. Up next, we have Professor Chris Lieben from Chrome City. Chris, are you there?
I am.
Fantastic. Right, I will stop screen sharing and let you take the lead.
Oh, brilliant. So hopefully, let me know that you can see me in a minute. If I do that.
Yeah, that's sharing.
Yep. Okay, great. Thank you very much, Mel. Thank you for also giving me the title of professor. That's not quite right, it's doctor. But my grandmother will be very impressed with the higher rank. It's a pleasure to be here. I'm really excited to let you know a bit more about what Chromacity does, what we've been doing over the last number of years. We are a company that I founded 7 years ago, specifically designed to develop ultra short pulsed laser systems. I originally started my career as a PhD student at St Andrews University, developing ultra-fast lasers for the telecoms industry, and then later moved to Heriot-Watt to continue the development of laser sources before we decided to spin out some intellectual property that had been developed within one of the research groups I was working in. And from that, I then was awarded an enterprise fellowship from the Royal Society of Edinburgh, specifically designed to develop Chromacity into what it is today. So as I said, we're 7 years old, we're now in our 8th year, and we have been developing a range of laser sources for a wide range of academic and industrial applications. And what I'd like to do today is to talk to you a bit more about the specific laser systems we've developed and how some of them have been developed specifically for some quantum technologies applications, some of which have been funded through Innovate UK schemes and others through our own technology roadmap. So the first slide that I have here shows the three main products that we now offer. If you focus on the product in the middle, the 1040, the Chromacity 1040, this is our core technology, and it's the original technology that we first developed. And the intellectual property that sits at the heart of this technology really revolves around the efficiency of the lasing process. And because of the high efficiency that we can produce from this system, we have the ability to run a system that generates less heat, so it doesn't need to be water cooled. It can have a smaller form factor. It has less components in it, therefore we can bring down the bill of materials and then transfer that lower price point across to the customer. So Chromacity's goal has been very much to offer laser systems across a range of wavelengths that are much more accessible to both the academic and industrial market space. And it's this 1040 nanometer laser system that also drives the two laser systems that sit either side of it here. So on the left, you have our optical parametric oscillators, and that is a laser system that can tune across broad, many wavelengths. And then on the right-hand side, we have some very specific fixed wavelength laser systems that operate in the green at 520 and in the UV at 350 nanometers. And I'll talk a bit more about those products because they were developed as through an Innovate project specifically designed to assist in quantum technologies. So I'll start with the 1040, and actually this leads to some of the comments that Yash made, because this system was originally developed for multi-photon imaging applications. That's where the company really started originally, and over the years we have gone on to develop higher and higher power versions of this laser system. So now we can offer 3.5 watts of laser light, which is considered to be quite powerful, specifically for microscopy applications. In a relatively small form factor, this laser system typically has the footprint of a large laptop computer. As I've mentioned, it's air cooled. There's no need for any sort of water cooling. So there's no sort of additional infrastructure that's required around these kind of systems. And what's really important here is that this is a part fiber, part free space laser architecture. And the fiber element leads us to be able to produce a very clean laser beam. So there's no sort of structure within the shape of the beam profile, which is excellent for when you're looking at generating wavelengths at other wavelengths. This is an ultra short pulse laser system. We can produce short pulses anywhere from 1 to 2 picoseconds, all the way down to now 100 femtoseconds. And these very, very short, intense pulses can be used to generate a number of nonlinear techniques, nonlinear processes across a range of different applications, some of which I'll come on to. As I've said, it's a laser system that we've tried to make affordable. We've tried to make it easy to use. We have a very simple user interface. And so far, we haven't had a laser system that's had to come back to base to be repaired over the last 7 years. So we know that we have good reliability, good robustness, and we're really pleased to see that. We've really tried to consider the engineering behind these systems. So we've got a number of technical benefits. I won't go through these in detail because I've got a lot to get through here. But essentially, we have ideal wavelength for a number of specific applications. We've got good stability. We've now got good high average powers for those specific applications, and we've got very short pulses, which meets the technical requirements of those. We've used those short pulses to then frequency double. You take the original wavelength and you divide it by 2, so 1040 divided by 2 is 520. So this is a green laser source, and this is a laser source that came about through an Innovate project in partnership with 2 academics at Glasgow University, who are both part of the Quantic Hub in Glasgow. And they came to us, and we had discussions revolving around the need and requirement to develop not only the green source that I'll talk about here, but also the UV source for looking at generating visible entangled photons, and latterly, more recently, entangled photons in the near infrared, so at 2 microns, and I'll explain why that is in a moment. So we now have this green source, which can generate 1.5 watts of light in the green. And we also have this UV source where we can generate certainly greater than 200 milliwatts. And the diagram on the left here shows the 1 micron source that we have in the white box, and then we have this small add-on module where you can frequency triple and frequency double into the UV. And the pulse durations from this type of laser source are shorter than 100 femtoseconds. And again, you can see the beam quality here on the right is nice and clean, nice and pure, which is necessary for the kind of quantum optics experiments that we've been carrying out. The first of which is a piece of work we did with Professor Daniele Faccio at the University of Glasgow, looking at photon pair counting. And this is a series of experiments we've carried out, as his research is very much pushing towards quantum imaging. Yash mentioned the ability to look around corners. That was a technique that was led by Daniele. And so he's now looking at the next step as part of that imaging process. And so he's now looking to generate entangled photons in the visible, so that they're easily detected by cameras. And so Chromacity supplied its 1 micron laser source, and we developed the third harmonic module. It actually requires the second harmonic module as well as part of that module. And so you have the Chromacity laser system here on the left, then pumping the third harmonic module, which generates UV light at 350 nanometers with power levels of about 50 milliwatts. And Daniele then implemented a special nonlinear crystal that down converts the photons. And what it means by that is it splits those high energy UV pulse, those photons, into 2. And if you do it correctly, then those 2 photons are indistinguishable. So they're considered to be entangled. And we ran a series of experiments here to prove that that is the case, that these photons are entangled. So if one of them is affected, you instantaneously know that the other one is also altered. So there are 2 benefits in generating this third harmonic laser light before you then create these entangled photons. So you have a 2-step process here, and there are advantages here. One is that the entangled photons you create at 690 nanometers, so that's in the visible, in the sort of the green region of the spectrum, are not going to interfere with your original fundamental pump light at 1 micron. And that's significant in terms of considering the signal to noise ratio. You want as much signal as possible, and you don't create many entangled photons in these processes. So being able to maximize your signal to noise ratio is key. The other advantage is that the avalanche photodetectors, so these single photon avalanche photodetectors that are indicated on this diagram on the right, have a very, very high efficiency in the visible, particularly the ES690. So you're going to maximize the chance of detecting these entangled photon coincidences. And this graph here indicates that that is the case. This large spike in the middle demonstrates that they have a coincident to accidental ratio, a CAR, as it's more commonly known, of the order of 100, which is very high, and demonstrates that we are able to create these entangled photons in the visible. And so the next steps are to look at the sort of Honger-Mandel measurements, which can be used to demonstrate genuine entanglement of these photons. So this is ongoing work that's taking place. We also have, we've been looking at working with another academic, Dr. Daniele Faccio, who is also at the University of Glasgow as part of the Quantic Hub, looking at generating photon pairs at 2 microns. So this is where we take the fundamental light from our 1 micron source and pass it through a specialist nonlinear crystal to then create entangled photons at 2 microns. And his motivation revolves around the ability to, or the want to detect entangled photons through the atmosphere. And this work has recently been published in Science Advances earlier last month, or later last month, just at the end of 27th March. And we're really excited by this work because it yet demonstrates the capabilities of the Chromacity products. And the reason this work is important is that when you're trying to do free space QKD communications through the atmosphere, you have to consider that there's a rather large ball of light in the sky that has the ability to interfere with your signal. And so the further away that you can push the wavelengths away from the main high brightness light that's being generated by the sun, all the better. And so the move towards a window near 2 microns where you can pass light through the atmosphere is of a huge advantage. And the piece of work that he's demonstrated has been able to indicate that very successfully, which has been brilliant. And so the graph, the image here on the left demonstrates this technique where you take the laser light, which is this red beam that comes in from the left, you hit this periodically poled lithium niobate nonlinear crystal, that splits the 1 micron photons into 2. So you then generate 2 photons at 2 microns, and he runs an experiment to prove that these 2 photons are indistinguishable. What's important about this work here is that he's had to use semiconductor nanowire single photon detectors in order to detect these photons, and these specialist detectors have actually been developed by Professor Robert Hadfield at Glasgow University, and a lot of his work has gone into optimizing these types of detectors, and he's been using one of our Chromacity OPO products in order to characterize these kind of detectors. So we've been able to demonstrate that we not only can create these photons, but we're also able to interrogate the system as a whole using the tools that come from Chromacity, which we're really excited about. Just briefly about our Chromacity OPO. This is a system that we've developed specifically for more sort of spectroscopy-based research. This is a system that generates 2 specific laser lines simultaneously. So you take the short pulses from our 1 micron source, you pump them into a specialist nonlinear crystal, and you then generate laser light across a range of wavelengths. So these are systems that, or we've got systems here that can split light across the sort of 1.4 micron region all the way up to 4 microns. So a huge advantage for spectroscopy. However, we have had academics who have used this capability, this laser system, to look at interrogating the next generation of quantum integrated circuits. One academic in particular, Michael Fanto at the US Air Force Research Laboratories, has been using our system to create entangled photons in the next generation of integrated circuits. We're really excited by this, as it demonstrates again the capability that Chromasti has to create laser light or across more exotic wavelengths. And so, in summary, this graph here on the right demonstrates the kind of broad bandwidth of lasers light that we can generate for a range of applications. We also have the laser sources in the visible and the UV, and we're keen to engage with the quantum optics community, because we recognize that we've got capability that we think has importance for future quantum technologies. So in that, I'd like to thank you again, and I'll hand back over to you, Mel.
Thanks very much, Chris. Really interesting to learn about photon pair counting, and seeing that you're able to demonstrate the creation of entangled photons there. So that's it from our speakers for today, but we do still have a panel segment coming up. Just bear with me a moment. So our panel, I'll share my screen. Our panel will be chaired by Dr. Martin Beaton, who's already been on earlier on. And the main theme question for the panel segment is, how can the Scottish digital sector capitalise on quantum capability? I just want to encourage you to submit questions into the question box on the right-hand side of the screen, because we will be trying to take 1 or 2 questions for the panel. In addition to the panel, we also have Dr. Petros Walden, who you haven't met just yet. He's a lecturer and assistant professor at the University of Edinburgh, where he works on the Quantum Computing and Simulation Hub and the Collaborative Computational Project for Quantum Computing. So I shall now hand over to Martin. I'm just going to stop sharing my screen.
Mel, while you're still on, obviously we're running towards time, but we started a bit late. So how are we going to push this till 3?
Yeah, we've got until 3 scheduled in with the initial invite. So as long as all the panelists are happy with that, we can go through to 3.
Can I also just throw in thanks, Chris, for that really interesting presentation. I also did my PhD in St Andrews, and my PhD, which was in chemistry, also pivoted on ytterbium. So there must be something about St Andrews and ytterbium. So maybe you and I were both in the same cupboard. It was at the back of a small, stinky cupboard in the chemistry wing. And I used mine to open epoxide rings in aqueous solution, and got a delightful paper from it. So I'm very proud of that. That's my one contribution to science. So
that's good to hear.
So yay for ytterbium. Anyway, we hummed and hawed about questions that we could put to the panel. What we normally do in EIT Digital events is we like to run the panel, and it's more exploratory. So ideally, it really involves the audience as well, everybody that's come along, to really just debate about a subject. It's not necessarily to pontificate or soapbox about particular. It's certainly not for lecturing. It's really to just talk around the subject. Now, personally, I would love if the questions could go down the line of entangled photons or particles, and is that the equivalent to a Star Trek subspace communication, instantaneous across the universe? I don't know. Or could a full quantum computer create a real-world simulation and are we actually living in a simulation? I know that's all old stuff for you guys, but I do find it fascinating. I love talking to my kids about it because it really weirds them out. However, I think we should probably bring it back round to more serious subjects. And so the first question we're going to put to the panel, and I say encourage questions from those that are watching as well. But really, in Scotland, we have touched a little bit on some of the brilliant work that's going on in Scotland, but how does it really compare with what's going on in the rest of Europe and maybe the rest of the world? So where is Scotland standing in your opinion? And is there anything that we are particularly good at in Scotland, something that we should maybe focus on if there are people who are looking at the more traditional digital innovation they're doing at the moment and thinking, right, okay, here's where I can engage because we have a particular strength here. So maybe put that to Petros, because poor Petros hasn't spoken at all yet. Thank you so much for joining us, Petros. Do you have an opinion on that?
Hello, hi. Well, thanks for inviting me here. Yes, so, first of all, I need to say, so my background is from a computer science department, unlike most other people that have spoken here today. So I would like to answer mainly regarding this question as far as quantum computing and potentially quantum communication is concerned. I can't say very much about the metrology and imaging part. So I think, as far as, I'll place first Scotland within UK and then within EU. So as far as computing, Scotland is leading in the software side. So something that is not mentioned very much is we mentioned a lot about building quantum computers, but there's a very little discussion of in this previous talks of what can be used this quantum computing power. Okay, we said it will be in the far future, some 20 years, but this is not quite the case. So the case is that in the next 5 years, we'll start having near-term applications, that these devices will not replace, as it was said, the classical computers, but there are already people considering applications in optimization or in chemistry. So there are industries that already have expressed interest, and there's a growing quantum software number of companies, startups, and that become bigger in the field. Now, Scotland and UK are in good place in this space, specifically as far as cybersecurity is concerned. So one of the things that is mentioned is that quantum communications may offer better security guarantees, but what is not mentioned so much is that quantum computing also has negative effects to cybersecurity. So one thing that even if the quantum computer is not there yet, it needs to be studied right now, and something that is being considered worldwide is how to secure, how to replace or how to secure our systems before these quantum computers come, and this is urgent. So it's already NIST in US, the Standardization Technology Institute. They have an active competition on replacing standard cryptography with something that is safe. Now, in order to establish confidence in any new, even classical crypto system, you would require quantum researchers trying to see the best possible attacks in quantum algorithm research. And there's big interest and big capability of Scotland in this respect. So this is one thing that I would single out as one thing from the computing side that I think is something to look into.
Thank you, Petros. Jeremy, if I could just throw over to you, but can also add, because I think you did make the comment about traditional computers are here to stay, but do we not have a problem with Moore's law is starting to fail? Therefore, something will need to replace traditional computers if we're going to keep needing more and more power to run emails and watch Netflix. I think you're on mute, Jeremy, sorry.
Sorry about that. So let's address that last point first. As Petros says, there are a range of applications for quantum computing, and they're typically problems that are really hard or it can require immense amounts of computing. But they're typically quite well structured. They're not sort of the general logic type, that's in your laptop or in your phone. So those sorts of, I'd say, general purpose logic devices, quantum computing is not the answer to that. Yes, I agree about Moore's law and at the ultimate edge. Yes, there's a problem, but realistically, we're going to need conventional computing, and we're going to need conventional computing to drive quantum computing for the foreseeable future. Thinking more generally about these questions of what should Scotland do? So Scotland is very strong, in my opinion, as we've heard, in the photonics, laser side. The components, those sort of that underpinning components, chromaticity, M-squared lasers. There's quite a few other laser companies, and these are critical for many of the quantum devices. But what we need to do is move up the stack of integration at the level of for the application to more of the application level. What are we going to do with them, and how do they become integrated into wider systems, if you like, the systems engineering of quantum devices? And that, to my mind, is where the real money will be made in the years to come. So Scotland's we've got to sort of kind of step up to that level of system integration level, and not just be known for the important role of just being the supply chain. So that's, there's probably some other aspects of quantum devices that will need more of a supply chain, and if we could grow those in Scotland, that would be good. That'd be simple. You think it would be simple, but it turns out to be quite difficult. Example are vacuum systems for many of these quantum experiments. Turns out to be really hard to make, say, quantum secure or quantum safe vacuum systems that actually work at the when we're down to single photons, actually work for these devices and keep a vacuum over a reasonable amount of time. So there's other supporting components. I think there's a lot on integration and moving up the stack. And also the great opportunity, as Petros has explained, is that start thinking about applications, particularly in the quantum world. We've got a very good start, some really quite strong groups in the academia. But I think that's almost like as a bit of a warning. Programming and taking advantage of some of the, particularly in the quantum computing side, requires quite a different thought process. But by thinking about it, you can make some fantastic progress. So, quite a long, bit of a rambling answer there. There's great opportunity, and but Scotland, I think, has got to move up its level of abstraction that it's aiming for in terms of the applications.
So, Jeremy, I take from that then that there may be an element of a missed opportunity right now. So we're not traditional computer or traditional innovation, digital innovation isn't harnessing the full potential of what's available in quantum. In a sense, quantum has moved a little bit ahead, and maybe people are still thinking in that old-fashioned mindset. So maybe we need to do something to encourage the incorporation of quantum capability.
I don't think there's a missed opportunity yet, because I think the quantum side isn't mature enough for that. But a few things are becoming that way. Some of the things that Ross described, and I touched on in the communication side, I think that's quite close to market. I think some of the sensors, are small and cheap, going to be small and cheap enough to be, useful, even in hospitals routinely, really quite soon. So in terms of industrial opportunity, those are the things I could see in the short term. But coming over the horizon are perhaps the more disruptive things, the computing side, and maybe some of the slightly more difficult sensors. I think the gravity sensors are quite hard to make. Rotation sensors, probably clocks are probably reasonably close as well. So there's a range of things coming here, but comms and some of the simpler sensors pretty soon, in my view. But that's my opinion. Others may have, a slightly different, a different view.
Thank you. If I could switch tracks a little bit and go back to what Petros. Sorry, Petros, go on. I was only going to, Petros, I was actually going to pick up on what you said about cybersecurity, and is this actually is this a global problem that we all need to tackle, or will significant countries end up in an arms race in order to get to the point where quantum and cybersecurity, is the first country to solve a solution which can crack traditional cryptography through quantum, or in fact protect their communications? Are they going to have some sort of huge advantage over other countries?
Well, that is the case, but it's less of a right now it's less of a concern whether you break the existing crypto systems with. I mean, the quantum computer that you require is not going to be built in the imminent future. So 10 years would be by far the shortest that one could imagine, and it's an underestimation. However, right now already there are developing classical crypto systems that are believed to be secure against quantum computers, and these products is like developing software for those applications is something that is an active area of research and innovation, and companies are involved in this thing. And this is probably one of the products that will be the first thing that we're gonna actually see on our computers. It won't be quantum in the sense that it will be a classical system, but in order to prove that this system is good, does what you want to do, it requires research from quantum companies. So there are a number of quantum companies that are doing quantum algorithm research, like Cambridge Quantum Computing and other, which they're not doing only this type of research, but the point is that this system, because they're classical systems, but they're approved by quantum research in a sense. So it sits in the middle between being a classical and a quantum product. So I wouldn't call it quantum technology necessarily, but it requires quantum technology expertise to be developed. And this is something that is really first time thing that we will see. Probably in 2-3 years, we might have in our computers replaced some of the current crypto systems that are based on factoring with some other that are based on, I don't know, lattice-based problems that are hard. I mean, this is not quantum technology, but in order to choose which of these you will determine, it requires quantum expertise, which can be developed by like companies that have such capability, basically. So this is just one example. Another thing, just to add to what Jeremy was saying and what other people said before, is as far as UK compared to the rest of the world and Scotland is sitting, is that we are we were the first country to develop this national quantum technology program back in 2014, and the first to launch this big Innovate UK type of commercialization of quantum technologies. And now we're establishing, there's a new center that is to be really opened today, well, not today, this year I meant, which is the National Center for Quantum Computing, which will be a big, some 100 million funding that will go exactly for this interface between companies and quantum computing research. So we have the Quantum Computing Hub that develops the hardware, and this is exactly the thing that companies that are interested about these applications would interact by this National Center for Quantum Computing. So I think that in this respect we're kind of leading globally. On the other hand, in terms of hardware, while we have very exciting research in many different approaches to quantum computing, with the ion traps, for example, being among the leaders, we are not as ahead as US, for example, in superconducting technologies. Of course, we do have, as Scotland, people working on this, for example, in the University of Glasgow, but we are not in the leading position. So yeah, so I just wanted to add this in the previous reply. Yeah.
There's a question that came in, we've only got a couple of minutes, so quickly, and the question is, how do the panel see the use of hybrid processors as a gateway between addressing the link between two worlds? So I guess some sort of mix between some quantum capability and traditional in one computer. Either of you.
Well, I think that at present, any quantum computer we can envisage requires really quite a difficult set of physical to building. The superconducting qubits require really quite very, we're called dilution fridges. They've got to be run very, very cold, and it's really quite hard to do that. So I think the thought of a paired thing of a quantum computer but networked with other something to drive it, absolutely, that's the way it'll run. I think my personal view is for many, many years it'll be cloud-based remote access. I think it's but I come back to what we've both said. We're going to need both types of computing for really quite a long time to make any of this viable. Petros, anything else you want to
add? Yeah, I want to add something. So if I understand correctly, the question was about hybrid classical and quantum computing devices. Was this related?
Correct. Yeah.
Yeah. So basically, when I said that we may have in the next few years some capability with this near-term, well, that are called also noisy intermediate scale quantum devices, these NISQ devices, is exactly the type of algorithms that people develop, including in Scotland and in UK, in our group, for example, is exactly algorithms that minimize the quantum part of an algorithm to the very minimum, to the thing that doesn't require long time coherences that we don't have, and pushes a lot of this processing power to a classical computer that can do this efficiently, and just takes the thing that the classical computer cannot do. So there's a big class of algorithms that exactly does this variational quantum algorithms that use both the advantages of classical computing and the advantages of quantum computing. And it's exactly this type of algorithms that I was basically talking about. And this is if we want a quantum computing application that is not going to be to the far future, this is exactly the place that we should be looking at. And this is the place that both researchers and quantum software companies are looking into.
Fantastic. That's thank you very much. Very interesting. And actually, as ever, the panels are way too short. I think we should, we could dig a lot deeper into the subject. However, we are at 3 o'clock, so thank you very much. I'm going to pass back to Mel now.
Okay, I just want to add on to what Martin said there. Mostly I want to thank all of our speakers that have come online today. It's been really insightful, some fascinating presentations covering a really broad range of topics within quantum. Also a massive thank you to our panelists and everyone that's been online. Please, can I just remind anyone that's been in attendance of the webinar to submit your emails if you'd like a copy of the slides. I'll just share our email address via which you can obtain those slides. So if you email edinburgh@eitdigital.eu, you'll be able to get a copy of the slides of the speakers. We also have a recording of this event, which we'll be sharing once it's been processed. And there's links to the event that was mentioned earlier on by Yash.